we're going. Put this over here. We are the circuit breakers, and this is our ping pong project. So our problem definition: medical crews need constant, accurate, and a simple way to get supplies to them in disaster scenarios. So with this, we did a custom research survey and we asked questions and we got answers. And some of the answers that we got were what building materials. So we could build it out of balsa wood, PVC pipe, rubber bands, dowels, small cups, and more. But those are the materials we used. The shooting distance, we have to be able to shoot from 2 feet to 15 feet. It went and how accurate it has to be. There's a target that we're gonna have to hit the size of a piece of paper. It has to be waterproof because there's a rainy scenario where the design will get wet, and it has to be triggered, no kicking, throwing, or pushing the payload. And there can be multiple tests, so it can't just fail after one shot. Requirements, which we got from the customer research survey: the design shall deliver the package from 2 to 15 feet, shall operate when wet, shall be accurate with the wind, shall have a small downtime, shall have a variable range, shall have no electronics, shall have minimal to no training required, shall have use shall use only the provided materials, shall be able to withstand prolonged exposure to elements and the minor impacts, and the design shall be triggered by a mechanism. In our criteria, we have accuracy, we have a target we have to hit, that's pretty highly rated. Speed, we had a question that was answered that was it should be rather fast and slow, but it wasn't really highly rated. Consistency, that's with accuracy, it can't be consistent. If you're not consistent, you can't really be accurate. So that was also very highly rated. Simplicity was a big part of this, and anyone needed to be able to use our design. So that was pretty highly rated. And payload weight was not very well weighted because we didn't really end up using it.
So before we started brainstorming our design ideas, we decided to do some research, which pertained a little bit to our criteria. Our first source dealt with projectile motion, specifically in parabolic motion. And this was to maximize our range and clear obstacles. Our next article was about wind drift and which projectile shapes operated best in wind and received the least amount of interference. And our third source focused on strength of different polygons that we could incorporate into our design to make it a bit more durable and resistant in disaster scenarios. Our first design was actually the design we ended up using as our prototype. This was a result of concept combo brainstorming, which was just a combination of the linear construction of a slingshot / ballista and the parabolic launch motion of a ballista, meaning it was able to launch a ping pong ball over obstacles and at a long distance because of the 45-degree angle, but it wasn't flinging things like a catapult, it was launching it like a slingshot. Our second design was a deployable ramp. This was a functional decomposition brainstorming product. Basically, we realized we didn't actually have to launch our product, we just had to deliver it in some form. And so this was a result of that. Basically, it had an extending platform that the payload could be rolled down and a variable geometry, which allowed the angle to change to meet the exact position of the target. This was, however, too complicated, and we scrapped this idea. And our last design was a bit more of a comedic approach. It was simply just a catapult with a rubber band at the end attached to a long lever arm, which would launch the ping pong ball a good distance. But it was a little too inaccurate and would have had a good deal of inconsistency, so we scrapped this design as well. Our AHP table lists our criteria by weight, which means by their importance. We argued that our accuracy and consistency were our top two priorities. It's pretty obvious why. You can't really have a product that doesn't actually achieve its goal. Simplicity was our third criteria. This was because it's usually a more reliable product if it's simpler, and also it's easier to use. Weight, as referring to the weight that the design would be able to launch or deliver, was our fourth priority. It wasn't a great deal, as one of our designs didn't even actually need any kind of wind resistance. And our last priority was speed and deployment speed, as deployment speed was not entirely the focus of this design. And if a product was slow, we could just incorporate two of the same product and stagger deliveries. And our decision matrix resulted in our choice to use our first design. As you can see, it scored the highest in all of or it accumulated the highest points. It had 7 in accuracy, 8 in speed, 7 in consistency, 5 in simplicity, and 7 in projectile weight, resulting in the highest score out of all of our products. These are our primary orthographic drawings. These were given to a different group, which would then assemble our product according to what they thought that these drawings would be. And as you can see on the next slide, Our final product actually ended up very similar to our drawings. The only difference was the side structures, which was interlocked with the main support for the tube, ended up being square instead of triangles. And this is simply really a cosmetic difference. Even though triangles are technically a sturdier shape, in this application, it's not that big of a difference.
So sunny conditions served as a neutral baseline. It didn't introduce any additional disturbances to the prototype. But when it came to the windy condition, the air from the fan significantly altered the ping pong trajectory, causing a noticeable impact on the distance covered compared to the neutral sunny readings. In the rainy conditions, the wet supplies acted as an extra weight for the ping pong, resulting in the prototype shooting the ping pong at a shorter distance compared to a neutral reading in sunny conditions. So to summarize, while sunny conditions were considered neutral, both windy and rainy conditions substantially impacted the prototype's performance. While a rubber band provides a straightforward and accessible launching mechanism, it's essential to appreciate its simplicity. Recognizing the inherent variability challenges us to explore innovative solutions. Although it may have limited adjustability, this invites us to think creatively about refining our design for the different scenarios. Acknowledging durability concerns motivates us to investigate material that can enhance longevity and reliability. Embracing these considerations as an opportunity for improvement will guide us towards developing a ping pong launcher that excels in simplicity and meets the demand of consistent accuracy.
Okay, we're using the empirical process. Using MATLAB, we created a graph using the empirical data. Then using MATLAB, once again, we found a line that best fits our data, aka the empirical equation. This was out of the empirical model. And as you can see within the bottom two images, the bottom image, or the very bottom right, gives us the full details of the original data. And then we plotted everything else on the image above. And it gives us the rainy day, sunny day, uphill data, the pullback data, and our x-axis and our y-axis measuring with the measurements and our plots. Moving further, predictive modeling as well. We have these up. We have our uphill data and we have our sunny day data, where the quadratics in purple are the best fit lines, and our data ones is our original data. With the top left, which is our imperial formulas, which is our equations. Same thing here, but instead they're cubic equations, and these are the ones that are best fit for our lines, as you can see from the data ones, which are the blue lines, and our empirical equations are on the top left once again. Same thing kind of here, but the final testing results uphill. We're given our quadratic, as you can see, and from our y axis, as you can see, our starting distance is from which is our distance to the target, which is equal to 8 feet. In our input, we're solving for that, which we got, which is x, which is equal to 7.5 centimeters, which helps us find our standard or our deviation. During the test, the predictive input hit the target the first time, but the rubber band loosened. So we switched rubber bands, and the rubber band was slightly tighter. This caused the largest inaccuracy of 12 inches. And when we then accommodated to the new rubber band, and by the last shot, we're back on target again. Furthermore, in conclusion, creating a design for this specific scenario required multiple design proposals before we settled on a final design for our prototype. Once our prototype was built, we ran multiple tests in various conditions and created predictive equations. We used to predict how much power we needed to launch the payload to our exact target, but this ended up in a degree of success with our design hitting the target 2 out of 5 times and barely missing it another 2 times. And that is it.